Hello students, our today's topic is all pair shortage path algorithm, which is from subject analysis and design of algorithm in fourth semester. Myself, I am Namdev, assistant professor in computer science and engineering department at IIT Bhopal. The content of today's lecture is introduction, process behind shortage, all pair shortage path problem, Flyod-Warshal Algorithm, numerical examples, which is based on each problem, and various applications of all the shortest path problem. So, before starting the shortest path problem, firstly we see the basics of from where these problems are generated, from which domain this problem is generated. So, firstly, we introduce about what is a graph. As we already know, a graph is a non-linear data structure that consists of the following two components: a finite set of vertices, which is also called as a node, is represented by V, and a finite set of ordered pair of the form U comma V, where U and V are two vertices called as edge. The pair is ordered because UV is not same as VU. In case of directed graph, there are two possibilities of graph: is directed and undirected. In case of directed graph, the direction is compulsory. This means if we have edge UV, uh, then uh, uh, then it is not compulsory that the V comma U's edges exist there. The pair of the form UV indicated there is an edge from vertex U to vertex V. The edge may contain weight, value, or cost. Here we see in this diagram where uh, a the diagram of graph we have seen here set of vertices where include A, B, C, D, and E are five vertices are here, and we have total six edges with respect to these vertices, which are AB, AC, AD, B, CD, and ED. We have also seen here each edge A, B, B. These contain some numeric value, which are known as the weight or cost of that particular edge. Now after basics of graph, we have to reach our main title, which is shortest path problem. As in graph theory, the shortest path problem is the problem of finding a path between two vertices in a graph such that the sum of the weight of its constituent edges is minimized. So we have to find the smallest distance, the smallest path between these vertices. The shortest path problem can be defined for graph whether undirected, directed, or mixed for directed graph. The definition of path required that consecutive vertices be connected by an appropriate directed edge. We have some variations of the shortest path problem. Uh, First one is the single source shortest path problem. In a single source shortest path problem, we have only single source, and we have to calculate the shortest path for the remaining all vertices, in which we have to find the shortest path from a source vertex B to all of the vertices in the graph. The solution of this problem is given by two scientists. First one is by Dixa and another one by Bellman-Ford algorithm. So and we have another variation for this graph, all pair shortest path problem, in which we have to find the shortest path between every pair of vertices B and V dash in the graph. Solution of this problem is given by Flyod-Warshal. Uh, there another also there are also another variation in which single source, single destination, and single source, single destination, and single source, single destination. So all these solutions also given by this in Bellman Ford. So our topic is to all pair shortest path problem. So what is all pair shortest path problem? The all pair shortest path problem is the determination of the shortest graph distance between every pair of vertices in a given graph. We have to calculate the minimum cost to find the shortest path. As we see in this example, we have Uh, we have 5 vertices A, B, C, D, and E, and we have to find the shortest distance between AB, between AE, between AD, between CD. Means all edges. We have to find shortest path between all these edges. So to perform these, we require a matrix representation by which we can store these values. So the solution of shortest path problem can be obtained by following steps, the following methods. First, we consider G as a directed graph. G direction of edges are given as. So the cost of the graph is the length or cost of each edges. And cost of I comma I means there is no concept of self loop. So in matrix, in cost matrix, you put I comma I is equal to 0. If there is an edge between I and j, then cost of if there is an edge between I and j, then cost of I comma j equal to length of cost of the edge from I to j. And if there is no edge, then we put uh, infinite there. Means we have no direct connection between these two vertices. We need to calculate the shortest path cost between any two nodes using intermediary nodes. Uh, we use following equations to calculate the minimum cost. A k I comma j is equal to, where k represent the intermediate nodes which path we have selected. So we have to, if you want to find the shortest distance between two vertices I and j, then we use k in previous stage. Where it result I distance between I and j, and if we include any intermediary vertex a in this path, then the distance of I comma k and a comma j. So we use this formula to calculate the shortest path between every pair of vertices. Uh, the solution of these problem is given by Flyod-Warshal. Is based on the following concept. Let the vertices of G be, here we take example, the vertices of G be 1, 2, there's 2 n vertices here. And we have a subset of vertices from up to 1 to k for some instance k. For any pair of vertices I comma j which are belongs to V, considered all paths from I to j whose intermediate vertices are all drawn from 1 to k is a subset of remaining vertices. And let P be a minimum weight path from amongst them. So here we see that the the subset which also include these vertices, but it is a subset of vertex set V. And P is a minimum weight path we have selected from every vertex to another vertex. The Flyod-Warshal algorithm exploits a link between path P and shortest path from I to J with all intermediate vertices in the set 1 to k minus 1. The link depends on whether or not k is an intermediate vertex of path P. So if we want to select the particular vertex, if, uh, if it is a part of path P or not, it depends on value of k. If k is not an intermediate vertex of path, then all intermediate vertex of path P are in the set 1 to k minus 1. Means we have used previous vertex up to previous vertex for this solution. Thus, the shortest path from vertex I to vertex j with all intermediate vertices in the set is also the shortest path I to j with all intermediate vertices in the 1 to k. If k is an intermediate vertex of path P, then break P down into I to k, k to j. Means we include K is an intermediate vertex which return the shortest path between I and J. Now we discuss the algorithm which is designed by Flyod-Warshal. We have include three parameter here: cost matrix, array A, and n is the set of vertices. So firstly, we initialize the solution matrix, same as input block matrix or cost matrix, or we can say the initial value of sorted distance are based on a shortest path, considering no intermediate vertex. Means the value which we have given of initial condition, we just copy into matrix A. So we have used two for loop here for I is equal to 1 to n and for j is equal to 1 to n. I represent the row and j represent the column value. So from cost matrix, we copy this value into matrix A. Now we add all vertices one by one to the set of intermediate vertices. Before the start of the iteration, we have sorted distance between all pair vertices such that the sorted distance consider only the vertices in set 0, 1 to k minus 1 as intermediate vertex. So all the vertices which are included in this path, we have to select all these intermediate vertex and find a sorted distance between. Try to find a sorted distance between these vertices. After the end of the iteration, vertex number k is added to set of intermediate vertices, and the set becomes 0, 1 to k. So before k minus 1, when we apply complete our iteration, so our set becomes 1, 0, 1 to k, where k is added as an intermediate vertex. For k is equal to 1 to n. Now we pick all vertices as a source one by one for by applying loop for I is equal to 1 to n. Now j is a select as a destination vertex by applying loop 1 to n. Now if vertex k is the shortest path, if is selected the shortest path from I to j, then we have to update the value of ai comma j by using the following formula: a of I comma j is equal to minimum of aij, and if we use k as the intermediate vertex, then we find a I comma k plus a k comma j. Means we include k as the intermediate vertex and find the distance if we trace the path with the help of k. And if the value which is returned, the minimum returned by any of value, then which is the final value of ai comma. So we have to apply all these on these values on all pair of vertices. Now let's take an examples. Here we give, as we seen in given graph, we have three vertices 1, 2, and 3, and edges are given between these. There's an edge between 1 to 2, 2 to 1, 1 to 3, 3 to 1, 1 between 2 and 3, and the corresponding vectors given. So we have firstly we create a cost matrix and copy into this matrix into my array A. So the matrix looks like so here we see there is no self group, and so the 0 at the diagonal position, and here we also see there is no edge between two. There is no edge from 3 to 2. So from 3 to 2 we have write infinite. So this is the initial stage of our cost matrix. Now we have to apply. Algorithm to calculate the shortest path between every pair of the vertices. So firstly we include. So firstly we calculate A1 will in which we omit column 1 and row 1, and check the remaining values for the shortest distance. So in this situation, yeah, A1 is the next equation. We have to find A2 comma 3 means second row, third column to find the minimum of A2 comma 3. So minimum of 2 comma 3 is A1 minus 1 as we see in earlier formula between 2 3, and if there is another path exists between these like 2 and 3, so we have seen here we reach 3 via with the help of 1 as an intermediate vertex. So a1 minus 1 from 2 to 1, and a minus plus a1 plus 1 from a1 to 3. So what we have seen here, a1 minus 1 means a0 cost of 2 comma 3 at a0 is 2, and cost of using intermediate vertex is total cost is 70. So we have find here minimum is 2, means there is no change in the previous value of a2 comma 3. We also apply same between a3 comma 2. So a3 comma 2 in a0, and uh, if we use 1 as an intermediate vertex, because we find there is a path between 3 to 1 and 1 to 2. So we include it as an intermediate vertex, and we find is in A0 3 comma 1 plus in A0 1 comma 2. So is A 3 comma 2 is we have given infinite because there is no, we have got 9, we have not found any edges. But if we use 1 as an intermediate vertex, then the cost of edge is 3 plus 4 is equal to 7. So we apply minimum function and we receive the shortest distance is 7. So we update our cost matrix A0 by putting these values into it. So the next expression A1 we find this cost matrix. Now we continue on. We calculate A2, in which second row and second column will omit, and we have to calculate the value uh, of A13 and A31. So in second iteration, A213 is equal to minimum of A A13 and A1, and same if we find any intermediate vertex 2 as intermediate vertex, so apply minimum function and we receive the 6 as the minimum value of from A1 to 3, or between A1 comma 3. Same we apply between 3 comma 1, and we find that 3 is the next updated value. So we use this and update the matrix, cost matrix second after second iteration. So the matrix look like this situation. Now we again apply iteration number third, A3, in which third row and third row and third column is omitted, and we use these four values for reduction or to find alternate options here. So what we have seen A1, A1 2. So to calculate A1 2, so calculate A1 2, we find we use just previous cost matrix here. So minimum of 1 2 is there, and if 3 is an intermediate vertex, so with the help of 3 we use these paths. Then we find that the minimum is 4 is achieved. Now we have again apply between 2 comma 1, and we have achieved 5. So we have again update cost matrix A2 by with the help of these values, and we find that the matrix looks like 0 4 6, and this will So this is the final cost matrix which contains shortest path between all pair of vertices in a given graph. Uh, Now the various applications of all-pair shortest path problems are like road networking, network routing, flight reservation, driving direction, and all but many more areas where we can apply all-pair shortest path problems. So this is the we'll meet in next lecture. Thank you, friends.